Hi guys, so the problem that we'll be discussing today is from the recent CodeChef Starters 9, and the problem name is Fibonacci Concatenation. So the difficulty level of this problem is easy medium, and its prerequisites are modular mathematics, and you also need to have knowledge of Fermat's little theorem. So now let us proceed to the problem statement. So let's read the problem statement. It says that let us define a Fibonacci concatenation sequence. So let f of 0 equal to 0 and f of 1 equal to 1. Then we have f of I equal to f of I minus 1 plus f of I minus 2. So this is a standard Fibonacci sequence. But here the plus sign, it does not represent normal addition. It represents concatenation. So for example, f of 2 will be 1 0. So f of 1 was 1 and f of 0 was 0. So if f of I is f of I minus 1 plus f of I minus 2, then f of 2 will be equal to f of 1 plus f of 0, right? So this is 1 0. So f of 2 will be equal to 1 0. Now similarly, f of 3 will be equal to 1 0 1. And yeah, so f of I denotes the ith Fibonacci concatenation number. So what do we have to do over here? Given an integer n, we have to determine the sum of digits of all subsequences of the nth Fibonacci concatenation number, which is f of n. And since this number will be large, it has to be done modulo 10 to the power 9 plus 7. So let us see a quick example. So just let us consider f of 3, or let us consider f of okay, let us consider f of 3. So f of 3 is 1 0 1, right? Now what are the subsequences of this 1 0 1? So 1 0 1, then 1 0 uh, 0 1 and 1 1, and then it will be 1 0 1. So yeah, I think we have covered all the subsequences. Yes, and also the empty subsequence, but it's not really worth considering this since it is not going to be contributing anything. So yeah, so the sum of this will be 1 plus 1 plus 1 plus 1 plus 1 plus 1, and total 8 ones. So the answer for n is equal to 3 will be 8. Now one thing is very clear over here, that since there are just ones and zeros, it is pretty clear that for all such Fibonacci concatenation numbers, all we will have is a binary string, right? Always a Fibonacci concatenation number will always be a binary string. So yeah, so this is a good observation to keep in mind. And so now let us proceed to the solution approach. So let's start with the solution approach. So first, let us try and see that how do we construct these Fibonacci numbers, concatenation numbers. So we know f of 0 is equal to 0 and f of 1 equal to 1. Therefore, we can see that f of 2 will be equal to 1 0, f of 3 will be equal to 1 0 1, and again f of 4 will be equal to 1 0 1 1 0. And similarly f of 5 will be equal to 1 0 1 1 0 and 1 0 1. So if you check the size, like the string size of these numbers, it is basically a Fibonacci sequence, because 0 is 1 1 2 3 5 8. So this is a Fibonacci sequence, right? Now it is pretty clear that we cannot actually check all the subsequences over here, because since it's a Fibonacci sequence, it will already be a large string, plus checking all subsequences, it is like it is an exponential operation, so it is not possible. So brute force over here will not work, so we have to try to do it smartly. So let us see for f of 4. So for f of 4, the string is 1 0 1 1 0. Now let us try to check all such subsequences in which this one will occur. So now a subsequence, you know, right, what a subsequence is. So over here 1 0 is a subsequence, and but 0 1 is not a subsequence over here, because we are going reverse, so that is not allowed. So subsequence is like we can delete any characters in between the numbers, so that is a subsequence. So let us try to check for this one, that in which subsequences it will appear. So first let us fix this one and let us take these as variables. So dash 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 dash. Okay. So let us see. So there are two ways for this 0. Either it will be included or it won't be included. So let us write 2 over here. Now for this one, again same way, two ways, it will be included or it won't be included. So again two ways, similar for this and similarly for this. So we can clearly see that this one will occur in 2 into 2 into 2 into 2, which is basically 2 raised to 4 subsequences, right? So this one will contribute 16 to the answer. Now let us check for 0. But since 0 won't contribute anything, there is no use of checking 0. So let us directly check this third one. So now let us fix this one first and let us mark the others as blanks. So again, this first one, either we will take it or we will not include it. So two ways, two ways, two ways, and again two ways for this one as well. So again, it will occur in 16 subsequences. So it will contribute 16 to the answer since its value is 1 itself, right? Now to this one, again it will contribute 16. So the answer for f of 4 will be 16 plus 16 plus 16, which is 48. So basically the formula is not very hard over here. So up for everyone there are size, so there are 2 to the power size minus 1 subsequences in which it will occur. Why size minus 1? Because size is the size of the whole string. So we exclude that particular one itself. So there are size minus 1 possibilities for it to occur. So 2 to the power size minus 1 for everyone. So everyone will occur in these many subsequences. So basically the total answer, so the answer will be equal to number of ones into 2 to the power size minus 1. As simple as that. So basically this is our answer to the question. Now the thing is that the implementation is a bit tricky. So now let us see how to implement this. So let us discuss the implementation. So the first thing that let us discuss that what needs to be pre-computed. Okay. So now there are two things that need to be pre-computed. First is how many ones are there in each each string. So basically in the first string which is f of 0, there are, so let us just name ones of 0. So ones of 0 will be 0. What is ones of 1? Ones of 1 will be 1, obviously. Now for 2 it will just be ones of 0 plus ones of 1. So ones of 2 will be number of ones in 1 plus number of ones in 0. And similarly we can have this recurrence relation for all the next numbers, because it is nothing but concatenation. So basically the number of ones in the previous two will be the number of ones in current. So we can say that ones of I is equal to ones of I minus 1 plus ones of I minus 2. Okay. Then the second thing is the size. So what is the size? So we have to pre-compute the size of the string. So size of 0, it is 1, and the size of 1 is also 1. Now what is size of 2? It is the size of 1 plus size of 0 plus size of 0. We can write the same recurrence relation for size as well, that size of I is equal to size of I minus 1 plus size of I minus 2. And with this we will have pre-computed like the number of ones in each number and the sizes of that particular binary strings. Now the question remains that what will be how to calculate the answer. So answer is equal to what is answer equal to? Answer is equal to ones into 2 to the power size minus 1. But there is a bit of problem over here because we need to give the answer modulo the mod value which is given to us 10 to the power 9 plus 7. Now over here, when we do mod, we assume that the exponent of when we use the power function in mod, so the exponent should be less than the mod. But since you know this is a Fibonacci sequence and it is not necessary that the exponent should be lesser than the mod. So here size minus 1 can be greater than the mod. So let us see how we can tackle this. We will be using Fermat's little theorem to tackle this. So what does Fermat's little theorem state? It states that a raised to m minus 1 mod m is equal to 1. Now this m is obviously a prime number, and the mod given to us which is 10 to the power 9 plus 7, it is also a prime number. So basically the theorem applies. Now what we are going to do is we are going to try and convert this 2 raised to sz minus 1 to something that we can implement. So let us say that sz minus 1 equal to k. Now we can write k as quotient into m minus 1 plus r. So what will be the answer when k is divided by m minus 1? So basically this. So it can be written as quotient into m minus 1 plus r. Now let us put this value into sz minus 1. So we had 2 to the power sz minus 1 right in our answer. So let us just put this over here. So let us put 2 to the power q into m minus 1 plus r mod m. So we were using the power function, so this modulo is necessary. So yeah, so 2 to the power so if we expand this, we will get 2 to the power q into m minus 1 mod m into 2 to the power 2 to the power r in mod m, right? Now let us revisit Fermat's little theorem over here. So here we saw that a to the power m minus 1 mod m is equal to 1. So this bracket is same as this, right? So the value of this bracket will be 1 because it is same like a to the power m minus 1. So the same thing. So the value of this bracket will be 1. So what remains with us is 2 to the power mod m. So what can we do of this? So now let us revisit here. So what is r? R is basically k mod m minus 1, right? Because if you divide k by m minus 1, then the remainder will be r, correct? So we can write r as 2 raised to k mod m minus 1. And what is k? K is nothing but sz minus 1. So this can be written as 2 to the power sz minus 1 mod m minus 1 mod m. So when we do this, then it ensures that the exponent is lesser than the mod, and therefore we can apply the like exponentiation that we do. So binary exponentiation can be applied over here. So the power function that we will be applying. So this is the trick with the Fermat's little theorem. And since we are doing sz minus 1 mod m minus 1, we have to also, when we pre-compute sz minus 1, we also have to use the mod as mod minus 1. So this is the implementation part that needs to be taken care of. Okay, so now let us directly proceed to the C++ implementation. So starting with the C++ implementation, here I have defined the two variables that we will need. So mod is 10 raised to 9 plus 7, and the maximum value of n I have defined it because I'm going to store the arrays globally. So maximum value of n I have given it 10 raised to 5 plus 5. Now these are some modulo functions that we'll be using. So this is addition with modulo, multiplication with modulo, power modulo, and These are the two vectors, one is SZ and one is ones that we discussed. So ones will be storing the count of ones for that particular number, and SZ will be the length of that binary string. So first we'll initialize that SZ of 0 should be 1 because 0 has size 1 and 1 also has size 1, whereas number of ones in 0 is 0 and number of ones in 1 is 1. So now we will run the loop from I is equal to 2 to I less than maxin. So ones of I is equal to, so I will be using the add function over here. So it is nothing but modular addition. So ones minus 1, ones of I minus 1 plus ones of I minus 2, just like we discussed in the approach. And over here SZ will be SZ of I minus 1 plus SZ of I minus 2. Only difference is here the modulo will be mod minus 1, just like we discussed in the solution approach. So this is the pre-computation function. So here we will call the pre-computation function. So in the main part, we will just take input n, which is the Fibonacci concatenation number that we want to find the answer for. And here I will just declare a variable answer. So here it will just be nothing but ones of n. So this will be the number of ones in the nth number into power of 2 to the power sz minus 1 mod minus 1. So this is just as we discussed the application of Fermat's little theorem. So basically we are writing nothing but ones into 2 to the power sz minus 1 mod mod minus 1. So this is the answer, and we will print the answer on a new line. So yeah, this was the solution approach, and I hope you understood it. I will also paste a link for you to study what Fermat's little theorem exactly is and its proof. You can explore that as well. So yeah, thank you.